So in this case, we should aware from how to write the conditions when the t will be equals to 0 and the t is equals to infinite. How I should write by applying by keeping in mind that is the initial condition, and how I can replace that in the equivalent circuitry is too important here. So R, L and C, and how the initial current which is flowing is 0, and how the voltage across the capacitor at the initial condition. So here the situation of your the short circuited and open circuited for the inductor and the capacitor is mentioned here. Now come to the next, that is the steps, how we can simplify before going to start the session, before going to start that numerical. What are the parameters you need to keep in your mind? What are the steps? What are the procedure you need to apply while you are going to simplify? That is important here. So see here, what is the procedure for evaluating the initial conditions? So whenever we are going to draw the equivalent network at t is equals to 0 minus, so before switching action takes place, obviously whenever the is 0 minus, it means that switching before the switching process, okay, and once the before the switching action takes place for t is equals to minus infinite to t is equals to 0 time period, and that will be the case under the steady state. Obviously the changes are not going to be happened, that's why we are saying that condition is nothing but at the steady conditions, okay. So and at that particular moment, the current which is flowing through the inductor will be IL 0 minus. Why we are taking before switching takes place, that's why 0 minus, okay. At a 0 instantly the switch will be closed, and 0 plus the current will be start to flow after switching. These are the cases. If inductor is there at initial, so IL will be 0 minus and voltage drop across VC will be 0 minus before switching. Okay. Draw the equivalent network at T is equals to 0 plus. Second condition will be you need to draw the equivalent circuitry by applying the condition of your the initial and the 0 plus. Immediately after switching, what will be the effect? This is the before switching, T is equals to 0 minus. This will be T is equals to 0 plus after the switching. Replace all the inductor with open circuited. The current will be IL 0 plus. See here the situation. Before switching, IL will be 0 minus. After switching, IL will be the 0 plus. And replace the capacitor or short circuit. Inductor will be over the open circuit, capacitor will be the short circuit, and voltage drop will be the VC 0 plus. Here was the VC 0 minus. See the initial final, you can say initial means before switching also you can apply, that is nothing but T is equals to 0 minus. Final means T is equals to 0 plus, you can say inductor, capacitor, open circuit, short circuit, IL is 0 minus, then later on IL will be 0 plus. Similarly VC will be 0 minus, then VC will be 0 plus. Likewise you can find the initial voltage and the currents in the networks are determined from the equivalent network at T is equals to 0 plus. Obviously whenever the switch will be completely closed and the current will be start to flow, then only it is possible to write the equation and we can determine the parameters related to that. Okay, if you're talking about the transient, definitely we are interested with respect to time period the equations of the voltage as well as the condition by considering by applying the conditions. Okay, so in the initial conditions, that is a di by dt is a 0 plus, dv by dt is 0 plus, d square I double derivative I by dt square 0 plus, d square v by dt square 0 plus are determined by writing the integration or differential equation for the network when the t will be greater than the 0. See here, 0 minus before, 0 plus after, and gradually when the time will be increased, definitely we need to find out all these four parameters, minimum four parameters, that is di by dt in terms of the current, dv by dt in terms of the voltage, d square I by dt square in terms of the current, d square v by dt square in terms of the voltage. See here double derivative. These four parameters we need to calculate when the t will be gradually increased, t will be greater than the 0 form. Now take the numerical number 1. All of you note down here. So what is that numerical? In the network shown below, the switch is closed at t is equals to 0. In the network shown below, the switch is closed at t is equals to 0. Switch is closed at t is equals to 0 with the capacitor uncharged. With the capacitor uncharged, find with a capacitor uncharged find the value of I comma di by dt and d square I by dt square. Find the I di by dt and d square I by dt square at t is equals to 0 plus. at t is equals to 0 plus. If you observe this equation, you will be able to find the network is there, that is with the component shown here, that is RC are connected in series along with your the sources and the switch, and the current is flowing in the closed loop. Fine. So now what we need to calculate here, we need to calculate the current, we need to calculate the current with respect to the time period, we need to calculate the current when the t will be 0 plus after switching. These three things are very important. The so voltage source is 100 volt, the resistor value will be 1000 ohm, the capacitor will be the 1 microfarad, and the current which is flowing is the I of t. Okay, and the switch is here. At present, the situation of your switch is open circuited. Here you may write here the S. This S is nothing but the switch which is at present open. Okay, so at the beginning, what they are telling, the capacitor is uncharged. When the capacitor is uncharged, it means that at t is equals to 0 minus condition is there. Obviously, capacitor is uncharged means the current is not started to flow. It means before switching case is there. So at t is equals to 0 minus comma, whenever the t is equals to 0 minus, the capacitor will be uncharged and the Vc will be 0 minus, and the Vc of 0 minus will be the 0, I of 0 minus will be the 0. Obviously, no current, no voltage before switching. Okay, this first step is nothing but before switching statement. Just because of that, before switching, neither amount of any current will be flow to that open circuitry switch, and the switch is not closed, that's why, and there is no voltage drop across the capacitor, both will be the 0. Now come towards the next. Once note on there, what is going on here, at t is equals to 0 plus, now second condition will be applied, that is after switching. So at t is equals to 0 plus, the capacitor will be act as a short circuited, already mentioned in the theoretical part. Whenever the switch will be closed, okay, the capacitor will be act as a short circuited. It's a mandatory to write that statement when the t at t is equals to 0 minus, at t is equals to 0, at t is equals to 0 plus, all these you need to mention. This is mandatory. What will be the effect of that on the capacitor and inductor, that also you need to write that statement, that is mandatory. So now how I can write my current, I is equals to V by R. I is equals to V by R. So I at a 0 plus will be equals to, what is V? V is the 100 divided by R is nothing but the 1000. So in this way, when the switch is closed, the current will be 0.1 ampere. The current is 0.1 ampere. I is 0 plus. Similarly, now once the current is this one, and after applying that condition, the capacitor, what we written here, the capacitor is short circuited. See here, the capacitor is short circuited, the resistor value, and the I of t is become as a I of 0 plus, and switch is closed, and 100 volt supply. See the difference, see the equivalent circuitry which is converted from the initial condition to the equivalent circuitry. See the changes. This is mandatory to draw the circuitry after the initial condition. What is going on once the switch is closed, what will happen? See the changes. Okay, so I of t becomes a I of 0 plus, R will be as it is, only the changes will be happen every time for the resistor as well as the capacitor, maybe the short circuit or maybe the open circuit. As per that only you need to write the equation of your the current. I is equals to, by the Ohm's law, V by R and all. Now come to the point how I can write my equation. So writing the equation, how I can write my equation in the form of the KVL. Writing the KVL equation for t is greater than 0. This is one of the condition. Then only it is possible to write the equation. What is that? Writing KVL equation for the t is equals to 0. So how I can write V minus IR is equals to 0? Already we have done in the theorems many times, superposition, many times in the KVL and the KCL, many times in the mesh analysis, nodal analysis, many times. V minus IR is equals to 0. So here how I can write, V minus IR is equals to 0. So it will be the similar to that only. So what is my V? V is 100 minus IR is nothing but the 1000 of I, minus again one of the what you can say, the component is there. So further it is 1 by C integral of 0 to T I of T dt. Already we mentioned it at the beginning. So 1 by C 0 to T I of T dt will be equals to 0. That is equation number 1. So differentiating the equation number 1, differentiate this equation. Differentiate this equation. So what will happen? This will become a 0. So minus 1000. Okay, this I will be become as a di by dt minus this 10 raised to the power will go up, 10 raised to the power 6 of I, this integral form. Okay, So we are doing the derivative form, okay, differential form. So in this way you will get this. Again simplify this one, di by dt. How many parameter we need to find out? We need to find out the I, we need to find out the di by dt, we need to find out the d square I by dt square, we need to find out the d square v divided by dt square, 4 parameters. So if you simplify this equation, you will get di by dt is equals to, what will happen if one side you are keeping di by dt, so minus 10 raised to power 6 divided by 1000 of I. So this will be equation number 1. So mention here clearly, at t is equals to 0 plus, at t is equals to 0 plus. So whatever you are having this equation number 2, same equation number 2 you need to write here, di by dt at 0 plus, because the meaning will change every time. If you're not writing anything, the meaning will change, because we are interested in at every instant, whether it's a 0 minus, whether it's a 0, whether it's a 0 plus. So it's a mandatory to write here. So di by dt at a 0 plus. So what will be the case? Why I'm writing here, I will tell you. 10 raised to power 6 divided by 1000 I of 0 plus. If I'm writing I of 0 plus, then only it is possible I can substitute the value of above, that is a 0.1, which I have calculated. Okay, so 10 raised to power 6 divided by 1000 you got, here will be my 0.1. Just because of this I of 0 plus, in this way I can get minus 100 ampere per second, so which is nothing but my di by dt 0 plus. See here the difference. If I'm not going to write anything, definitely I will be unable to find out these unknown parameters of your di by dt and all. So you should remember why I'm going to simplify these things. First KVL, then differentiation, then apply the condition of t is equals to 0 plus. So in this way equation 1 and 2 will happen. Now again double derivative, differentiating the equation number 2. First we have done the differentiation, now go for the differentiating the equation number 2. So what is my equation number 2? This is nothing but my equation number 2. So d square I by dt square is equals to minus 10 to the power 6 will be as it is 1000. This I will become as di by dt. This I will become as di by dt. So what will happen at the t is equals to 0 plus? D square I by dt square 0 plus is equals to uh, d square I by dt square 0 plus is equals to minus 10 raised to power 6 divided by 1000. This di by dt of a 0 plus. Why I am writing again? If I'm not going to write I of 0 plus, I will be unable to write here the answer. Again, if I'm not doing the di by dt, I will be unable to write this answer which I have obtained here. So just note down di by dt 0 plus. So then only it is possible to substitute the value of that, that is minus 100. So in this way these two will be cancelled out, this will be cancelled out, you will get 10 raised to the power 5 ampere per second square. Ampere per second is the double derivative, just because of that double derivatives it will be ampere per second square. Here will be ampere per second, here will be the second ampere per second, ampere per second square. So likewise we can simplify. Before going to start, be remember the steps, be remember the initial condition, apply that initial conditions, whether it will be related to t, that is a 0 minus 0 0 plus, whether it's related to the short circuit or open circuit, whether it's related to the writing the equation in the form of the KVL. Each and everything you should remember, even you need to draw the equivalent circuitry. Okay, go for the next numerical number 2. What is that? So in the circuit shown below, the switch is closed at t is equals to 0. All of you note down fast. In the circuit shown below, the switch is closed at t is equals to 0. First stop, with a zero current in the inductor, with a zero current in the inductor, with a zero current in the inductor, find I, comma d by dt and d square I by dt square. Find the I, di by dt, comma d square I by dt square at t is equals to 0 plus. At t is equals to 0 plus. The circuitry is shown in the shown in the numerical, that is R and the L is there, that is nothing but the resistor and the inductor both are there. Previously the situation where the capacitor was here, here is the inductor, so along with the resistor. So RC numerical we have solved. Now the RL numerical we are going to solve. The switch is there, the current is flowing and the voltage is across